Okay, welcome everyone for another quantum team round table style meeting. And today I'm planning to to discuss a little bit about Bohm-de-Broglie interpretation, and I'll talk about the measurement problem. So I'll try to make like a comparison between the how Copenhagen interpretation, Copenhagen view interprets the results that we obtain with the Bohm-de-Broglie interpretation, make the comparison between both. Because the math is basically the same. So let's let's start sharing here. Okay. Okay, so let's start. So another quantum T. Still second part that we'll talk about Bohm-de-Broglie interpretation, but specifically I'll talk about the problem. That's the measurement problem. So let's first some slides to to say a little bit about some things about the measurement problem in quantum mechanics, and we discuss a little bit the interpretation, the Copenhagen interpretation, and then the von der Broglie. So questions involving the measurement of a quantum observable and the frontier between classical and quantum are controversial subjects in quantum theory. The collapse postulate says basically that the only possible result of a measurement of a physical quantity is one of the eigenvalues of the corresponding observable. However, some people say that this is just a way to avoid a deeper discussion about the thing. So we have the result, and we have this postulate, this collapse postulates that say among all the possibilities that the wave function gives to you, the wave function collapse, and the result that you obtain is the result of this collapse, this specific place, let's say. So Bohr basically says that since our minds works classically, the concepts that we understand and can communicate are classical. Thus, a scientific theory should be formulated in classical terms. So the measurement apparatus is classical as well, and the measure is just the interaction between these apparatus that is classical with the quantum object, say electron, for instance. So in this context, Bohr said that the corpuscular and wave nature of a quantum object are complementary attributes. That has the name today from the complementary principle. Okay, so in the case of the double slit experiment, if we determine from which slit each photon passes through, we identify the particle attribute and destroy the interference field. So the wave attribute is lost, it's just lost. In this view, the wave behavior for macroscopic objects is not seen since the masses are too big, the masses involved. So consequently, the Broglie wavelength is small. For big masses, h is the Planck constant, v is the velocity, p is the momentum, and lambda is the wavelength of this quantum object. So for big objects, m is big, and so lambda is small. In the case of a photon, if you have like big wavelengths, you have like small frequencies, and the energy of photon is given this. So, however, this interpretation is contested by many people, usually with this argument that is, if everything is formed by atoms, so in what moment does it need to see the characteristics of the quantum world? So, where is the border in between the classical and the quantum world, according with this view. This is not this is like an open question. So people try alternatives to, where this question will not appear. So Schrödinger and Wigner consider fundamental questions related to the classical limit. And these questions is related with the Schrödinger cat and Wigner friends that show some ambiguities related to macroscopic objects in this, when we consider this real Copenhagen interpretation view. But it was like von Neumann who tried to describe the quantum process of a mixture with a postulate. That's the collapse postulate that we mentioned in the beginning, related to the wave function. So basically, the math that I will show here will be quick, and it works when we talk about like the Bohm de Broglie as well. So just a little bit about the measurement problem using like the von Neumann's argument. So if you consider operator S an observable that will be measured, and Si the respective n states, so you have this relation. You have this Si here is just the eigenvalues associated with S. So the eigenvalues are discrete in this example, where n is the total number of orthogonal eigenstates. Okay, and consider now X, the cat X, the eigenstate of the position operator, which is linked with the center of mass of the measurement apparatus. Okay, so this is, you have this relation, the X applied to the eigenstates cat X will give the result, the eigenvalues X small x. So the interaction between the system, the quantum system, and the apparatus that is classical is given in a finite time interval. In a time interval where both do not interact, the system is said to be isolated. Okay. So if we write the state of both systems, we have this. So the psi is the state that relates the quantum system and the classical apparatus, right, in this way. So each one belonging to their own Hilbert space, okay? And the interaction or measure will introduce a correlation between both states. Okay. So note that if the initial state of the system is eigenvector from S, the measurement will not change, but will modify the state of the measurement apparatus. And this modification will be something proportional to the eigenvalue that corresponds to this eigenstate, to the S. In this way, we can define like a evolution operator, like given this way, that Ui is given in terms of the exponential. Lambda here is defined in this way, in terms of this function, g of t, where g of t is a non-null in the interval, in this small interval, t. S is the operator related to the quantum system, and P is the momentum operator that's related with the position by this relation. So this interaction must change the initial state, the state before the measure, to a final state, the state after the measure. So in this context, we can define the Hamiltonian in this way, and we can apply this guy here to a state like that, just to see how it works here. Here's the steps need to get the result. I mean, it's not so important to us to see all the details here. Just like direct some typo here, okay? So it should have here a plus and 3 points here. So the result will be something like this. When we apply this evolution operator here to this state, you have something like that, where this x plus lambda si appears because this guy here can be viewed as a translation operator. In quantum mechanics, just to review, a translation operator is the one that, when applied to the x eigenstates, it like shifts the x eigenstate by a quantity that's proportional to the x. In this case here, the who make the wholes of the dx is this guy here, lambda si. So you could think this like that initially the system was like centered in a not here. Yeah. Okay, so this is the this result. So let's apply this to what becomes. Now, if we take the following state vector as the initial state, like psi 0, let's call the initial state, in terms of phi of s related to the system, and phi of a, that's the state related with the apparatus. So if we use like the superposition principle, so this is all the possibilities that we have for phi of s, and these all the possibilities that we have for phi of a. Okay, this is discrete, and the space here, the position here is continuous. So if we apply this thing here that we did initially to this state now, if we follow the same steps, we will find that psi of f, so after the interaction, we'll have a state like this, where psi of f, when we use these results here in equation 3, we'll find something like this, where phi of a now is a function of s, I, and then given by this. So initially, the function, if you could think about this f of x as a Gaussian function, for instance, that is centered around like x equal to 0. Now it was like shift by a value. It's centered now around like lambda si. That's the state after the initial. Okay, so this equation 4 tell us that when a measurement finish, only one of the several possibilities from the initial system appears as a single result. So which is the measurement result? So for example, this psi of f could be written in terms of the collapse of each. Could be written in terms of the superposition principle of each ci. So this will be like the total wave function. But when we make a measurement, let's say if you measure C1, so all the other possibilities will collapse and we'll have only this possibility. So this is the Copenhagen interpretation. Among all n possibilities, the wave function collapses to the result indicated by the measurement apparatus. That's the collapse postulate. Okay? So this is the Copenhagen view. Okay, but the problem is that this collapse is never directly observed, and this gives rise to different interpretation. So today, to opposite view to this Copenhagen interpretation for the collapse is the Bohm interpretation. That they basically say that the collapse is just apparent, and in this case, just one of the possible eigenvalues, Ci, will be different from 0 in the specific position, x of I. where the pointer of the apparatus is placed. The other C, that's called Cj, where J is different of I, are not present in this position xi specific. And the wave functions associated with them are called empty waves. And this position, xi, is unique and depends only on the initial configurations of the total system. That is the same, like you follow like the Schrödinger equation, and we'll find specific psi associated with it. It's the same, basically the same from the Copenhagen interpretation. The only difference is that the psi, as we discussed in the last meeting, is that the wave function now you can like evaluate the trajectories, different trajectories associated with the particle. Okay, and here that there exists an objective reality in this case, associated with xi in the degrees of freedom from the physical system, plus the apparatus on the configuration spaces. However, we do not know the initial configuration. We only know its distribution that obeys basically the Bohm rule. And thus we can only evaluate the probability of Ci to be selected, and the empty waves cannot be detected by the other apparatus. At least the way I view here, this probability that appears here is like the classical probability that like we have, because we don't know all the possible configurations initially. So that's why you have the probability here. But we have like an objective reality. It's not a collapse that happens. It's something similar to a collapse. It looks like a collapse, but it's not, at least in this view. So just to finish, let's see an example, and we open to discussion. One example based on the von de Broglie interpretation. So let's consider that after a measurement, we have like a psi that's called psi f of x, which can be written in terms of psi1 plus psi2. This x here is not the position, it represents all the degrees of freedom from the physical system in the detector. Now consider that we add two extra detectors, one each region, one in region 1 related to psi1, and one to related in region 2 that's related to psi2. And that's called the wave function associated with these detectors, like phi1. Sorry? Okay, phi1 y, and in the region 2, phi2 of z. Okay? And these, again, y and z here are just like letters. I mean, it doesn't mean necessarily the position. It's the degrees of freedom associated. So before the interaction of this function with these extra detectors, we have this total wave function, initial wave function, that I'm calling here psi of I, x, y, z, that is given by this one, times the other two. Okay. So after the interaction between psi I and the detectors, we have this psi f, which is given in terms of this var phi 1, that is the relation between psi1 and phi1. Okay, so that's why I call here var phi of x and y, and this var phi 2 of x and z, that's the interaction between psi2 and phi2. So where phi1 xy and var phi2 xz are entangled states resulting from the interaction that happened in region 1 and 2 respectively. So note that the interaction between psi1 of x and phi1, that's related to this var phi xy, cannot affect the phi2 of z, cannot affect this other term here. This is because the locality of each interaction. So each detector is in one position different. So if the particle is present in region 1, in equation 5, let's say, region 1 here, the wave function psi2 is an empty wave, and it will still be empty in equation 6. So it still be empty here. And thus detector 2 or phi2, this phi2 here, will not click. So it be like 0. In this case, the detector 1, where the particle is placed, is the only one that clicks. So this will be different of 0. Thus, for the total system, only region 1 is noticeable. So interaction with the environment during a measurement procedure separates the wave packets in the configuration space, each one in each configuration space. That's the case of equation 6 and 7. This, each one was with a specific wave function, which is where apparent wave function collapse comes from, even though there is no actual collapse. So we do not have a collapse, but it seems that it has happened in one in this case. Because objectively, the particle was, in this example, was always here, psi of 1. We can write the psi in terms of all the possibilities. But in the end, the detector will tell you, oh, it's here in psi 1. Because it was always like in this example here, it was always there. But it seems that we have like a collapse, but it's not the case. So this is the references, and yeah, we can open for comments and discussion. So basically, at least in the part I understood, is this, like in the Copenhagen, we have this probabilistic interpretation since the beginning. We have all the possibilities on the wave function, but then it collapsed to one. Here, no, you have like one real objective, let's say, position for the particle, but it seems that it has some other possibilities. The thing is, the particle was always there, always in this region, like psi 1. The region associated to psi 1. So, okay. Questions?
Yeah, Carlos. So what you're saying is the system is almost like a lottery. In the first interpretation, all the tickets are in the box, and you don't know which ticket's going to be picked until you pick it. In the second interpretation, there's only one ticket in the box, but you don't know what that ticket is until you pick it.
Yeah. Yes.
Yeah.
Yeah. In the first case, if you try to pick it to the ticket, you can the second time take a different ticket, right? Because it's all the wave function could collapse to another side,
right.
Side 2.
In the second case, you've only got one choice. You're going to pick the one ticket.
Yeah, since the particle, let's say, the ticket is really there in the second choice, because it could be different, because you have another interaction between in the second round, you have another interaction between.
Right. But you just don't know what the value is until you check it.
Yeah.
But it's not changing. It's always the one value. Huh.
This way I'm seeing, I'm understanding.
I have a question about the formalism. Initially, Bohr had said that the apparatus is classical, but then you go through some computations as if the apparatus also had a Hilbert space and the quantum
Yeah, it try to represent quantically how this is, because you associate an operator, the x of the position, right? The position of the apparatus, but the apparatus as well is like the position is related. The position of the apparatus is related with that operator.
Okay.
But the apparatus is classical, and but it has some position, and in this position you associate like an eigenstate. So some other questions, comments, or criticism about this view as well? I still like following each step, so I don't know. I know that this has problems. At least I read, but I don't understand well. This interpretation has problems in the relativistic. When you consider the relativistic theory, it seems that it has some problems that people could not fix as well. I mean, until today. But it's a kind of thing that I need still to understand. But yes.
Yeah, one question I have is about the apparatus itself. Okay, so say you had two apparatus that could take the measurement.
Yeah.
And the first time you use the first one, right? You repeat the experiment using the second apparatus. Does that change anything?
I think the idea is it's like the second apparatus, like because okay, you have the first apparatus and you have like, but you need something to read this first apparatus, right? You need something that related. That's why it's like the second apparatus, at least is in this view. You have the result that is in the first apparatus, but okay, you need to read this apparatus.
Right.
That's people call it. I think they forget like the name. It's the cascade apparatus problem, something like that, related with the von Neumann. Maybe something. But that's the idea for the second apparatus. Like you have the result, okay, but you need to read this result that you obtain. And then was in this example.
And so I guess over the last 100 years, nobody has come up with any way of testing the difference between these two interpretations.
Yeah, I don't because it's like it seems to be like the same, you have the same math. The interpretation is different, but what's the
results will be the same.
The results will be the same as well.
What happened?
I mean, the difference was like in the last section that you have like the trajectories, but how will we measure the trajectories? That's the problem, because if you measure, you need the apparatus to measure. You have the Copenhagen interpretation. Okay, so you lose like the wave interpretation. You have like the particle because the wave collapse. But if you are from the Bohm de Broglie, no, it was there always, but you cannot make the difference. It collapsed, or it was always there. Always was like in this place when you measure. That's the thing. I mean, both are still possible, and it's a question of how you prefer. But it seems that it has some problems in this interpretation. At least I'm not really sure, because I never study in details to see what's the problems. It seems it has some unsolved questions related with the relativistic. When you take like special relativity together, like in quantum field theory, some results it seems it cannot. get the same results. But it's I think in the future maybe we discuss. Yeah, but until so far, at least we are still like in the 50s, like in the Bohm de Broglie interpretation. It seems that you have the both possibilities. Then came like Everett in the late 50s with another third possibility that the mean wars interpretation. And Bell, I think, is in the 60s, early 60s, right? With the that try to make the difference between like the Copenhagen and these hidden variables interpretations. That is related here. Remember the past meeting we had like is the math of human space at all extended to other structures? Let's see the questions. The question from Mohammad Riza here is good for the math, could help. Is the mathematics of quantum mechanics, Hilbert space, at all extendable to other structures? And if there are varieties of these, maybe one can incorporate this interpretation into different math structures. Well, I know that like you can use like this at this. It has problems and then we put gravity, right? That's the problem of quantum gravity that relate like quantum mechanics and general relativity. But if you don't consider gravity, yes, but I don't know what you mean exactly by all extendable to other structures. I don't know if in the mathematical point of view what it really means. The math guys has some comments. Bob, George.
Yeah, I'm not sure what Mohammad Reza means by. Oh, he has more comment.
Some more complicated structure that contain Hilbert space. Some more complicated structure that contain Hilbert space.
That's a very intriguing idea. But I'm not sure where to go with it.
Sorry, maybe it doesn't make sense. Sorry. It's,
no, just
mm,
at least I don't know if this is my first comment answer your question. Like when you put gravity, it has some problem incompatibilities between quantum mechanical and general relativity. So at least in this case, it doesn't work. But if you forget gravity, you cannot worry about that.
so this,
So yeah, because I'm not sure about what really means like complicated.
this question was just about mathematics.
Yeah, Mohammed, if you're trying to talk, we can't hear you.
Sorry, I didn't hear you. I lost connection.
Yeah.
Okay, yeah. It don't.
I mean, mathematically, more general structures would lose the nice properties of Hilbert space. So you would need to gain something to make up for that. You know, you would lose maybe uniticity or self-adjointness or even closure. That's a difficult question.
Yeah. Unless you'd be looking at something where the Hilbert space is like a sub-Hilbert space or something else.
So there is no structure right now in mathematics that can accommodate Hilbert spaces in something, I don't know, bigger, I don't know, maybe more complex, that can be mathematically viable, right? Is that a correct conclusion?
Yes, or rather that we don't know really much about such structures, except that the nice qualities of Hilbert space would be lost. I mean, even if you go to Banach space, you lose the inner product, and so you lose all of the formalism about rotations.
Yeah, exactly. For example, in the opposite direction of Banach spaces, something that perhaps a simplified version of that would be a Hilbert space, such in the case that Hilbert space is a little more that is.
It's intriguing, but I right now, without a lot of thought and research, I don't know. So I find that a very fascinating question, but I can't answer it.
I guess my question on this be, would by extending the Hilbert space into a more complicated space, how would that help us tell the difference between these two interpretations?
Yeah.
No, I guess I think I'm not sure, but when the structure is a little bit more complicated, they can sit in different varieties. I think the interpretations and the predictions would be different. I'm not sure, obviously, but I guess there will be a probability that this will happen, and this will be helpful, really. And the other points regarding quantum gravity, I don't see any point in deriving
We lose your sound, Mohammed Reza.
into the square.
Yeah, at least I can
help
listen.
very much.
I can listen. Yeah, could you repeat the part of quantum? We were talking about quantum gravity, because we, like, at least I didn't listen, didn't hear you.
Yeah, okay. So in quantum gravity, we say that if you, for example, mix relativity with quantum mechanics, many of these interpretation problems will disappear. I think this is the principle help solve the problem. Quantum mechanics in and of itself should be coherent enough to address these interpretation issues. I don't think, this is my opinion. I'm not sure if it's
I agree. I agree. It should be like self-contenting.
Yeah, exactly. Yeah.
Any more comments? But good, nice, Mohammed. It's a nice point. So, is there a more general mathematical, if I understood that, is there a more general mathematical structure that could help to make the difference? between these interpretations. Yeah.
Yeah, it's kind of an interesting concept. You can build these structures specifically designed to test these two interpretations, and then see if that structure somehow fits reality.
The analogy I could make would be with Euclidean and non-Euclidean geometries. They can both be interpreted in a larger context of, say, Riemannian geometry. So, in that sense, there could be a larger mathematical theory that includes both, but I have no idea what that would be.
You gave me another thought, which is looking at our basic assumption. We're assuming it's one or the other and not both. I mean, it's possible that the solution could have a component that is fixed and a component that's variable, like an intermediate, like a hybrid interpretation of some kind.
Yeah, I don't know if some because there are a lot of other interpretations, right? Maybe some of them are like hybrid, but I'm not really sure.
Yeah, because right now our discussion, we're assuming that either it's totally probabilistic or it's totally fixed. We just don't know which until we measure.
Yeah.
Maybe there's an in-between ground, where in some cases it's fixed, in some cases it's probabilistic.
Yeah, I agree. Yeah, in many words, it says that you have, at least the things that I read so far is like, okay, you have all the possibilities, and all the possibilities are measured, but in different words, right? Not if we measure, like in this example here, the region 1, you measure that the particle is there, and another word is what is measured that the particle is in region 2. That to me, we still have the. I don't know if this is something. I think it's not something in between, Bob, because like it seems like it's real, the positions, but the probability, the Copenhagen, the only difference that we don't have like the collapse. Right? Oh, you have the collapse, but in each universe it collapses in different way. I don't know how people see this. I don't know, it's something in between, Bob, as you were like mentioning. Okay, some other comments, questions? I'm planning like the next. I don't know if I could like follow in with this, or like we still didn't discuss about the spin of the particles related to this, how Bohm de Broglie see the spin of the particles. Maybe it would be nice, like in the next, we discuss a little bit about this, and then after we discuss about the spin, and we could like start like the view from Everett, like the main word interpretation. But I'm thinking a third part from the Bohm de Broglie would be nice too. What you guys think? Like discuss a little bit about spin. What do you think, George? Or you prefer like maybe go to
There is one mathematical subtlety, which is that the Bell equantity or von Neumann's disproof of hidden variables only applies to local hidden variables. That von Neumann's proof does not exclude global hidden variables.
yeah.
And that's something I'm still trying to understand. Well, I'm still trying to understand the Bell inequalities. So there's definitely a lot there, and historically, definitely, Bell was inspired by taking seriously the Bohm de Broglie interpretation.
Yeah, I think he was like at least in principle favorable
Yeah,
to the interpretation, and was thinking a way like to test.
yeah. It's the history is really fascinating. How it really kind of just got put on hold for like 40 years between Einstein and Bohr and them in the 20s and Bell in the 60s. There was this attitude that this is not physics, it's not math, it's philosophy and should be ignored.
Yeah.
But here we are today.
Yeah, but I'm thinking the next, like before we get like to many word interpretations, we still discuss a little bit more about like spin, how the von de Broglie see the existence of the spin of the particles, and maybe we could like finish this, and then the other go to the in 4 weeks we go to many words.
Yeah, I think that would be good because I still have a sense that the classical optical double slit experiment isn't quantum at all. It's Young's wave experiment.
Yeah, I think it'd be. I think I have an example that's related with the Stan-Gallop experiment.
Yeah, the spin there seems to be more intrinsically quantum. So that would be interesting. Seems like the whole, if I'm understanding the Bohm, de Broglie-Bohm interpretation, they're trying to combine the wave and particle by having the particles be real and having this pilot wave shepherding about.
Yeah,
Aside from interpretation, I don't see how that's actually any different from Schrodinger's wave equation.
yeah, because the Schrödinger equation is deterministic, right? The
Yeah.
problem is the after. It gives only the wave function, and the wave function in principle is the modulus square that has meaning. That is the probability, density probability of density.
So
But I think yeah, but I think they try like to give like because okay, so the Schrödinger equation is deterministic, and they has the psi. You can like evaluate the psi, and the psi in this Bohm de Broglie, you can with the psi you can like evaluate like the velocities of the particles.
Yeah.
And then we have like the trajectories that we saw in the last meeting. But I mean, we are the thing is, it's a question of interpretation, at least here so far that we discussed, because when you consider quantum field theory, it seems to this interpretation has some problems, but I still don't understand well, like the Broadway-Bohm interpretation.
And arguably, quantum electrodynamics and or quantum field theory have their own problems.
Yeah. Yeah, but okay, so in 15 days, probably, like we are back to discuss a little bit about spin of particles and see how Bohm de Broglie interpret. What's the difference? I still don't know. I need to see this. The difference from their view with the Copenhagen interpretation view.
Yeah.
I think it's a nice thing.
Definitely appreciate your doing all the groundwork to lay this stuff out ahead of the discussion.
Okay, it's good because we learn different things.
But yeah, we are coming up on the hour, so thank you.
Yeah.
Thank you also Bob and Mohammed Reza for intriguing contributions.
Yeah. So thanks Mohammed Reza and everyone, like Barry and Claudia as well. So Diego has some problems. He leaves during the presentation. Okay, so I will stop the recording now. So see you guys in the next not in the next, in 15 days.
Yeah.
Another Thursday. I think is in the 20 maybe. But we will send the message telling when it's the next. So probably the 20 of March.
Yeah.
So see you guys there.
Bye for now.